So here we have a function, and we've been told that we need to calculate the gradient of it at this point here. Problem is, we don't really know how to find the gradient of a curved line. All we know to do with gradients is this old formula. Rise over run. M equals y2 minus y1 over x2 minus x1. Now this formula is fine. This is going to get us the gradient of a function, except it's really only going to work on a straight line. So we think to ourselves, okay, let's get ourselves a straight line. And maybe we'll make a second point up there, and we'll make those 2 points our y2 and x2 and our y1 and x1 here. Now, if we're going to go and calculate the gradient of those 2 points, essentially what we're doing is calculating the gradient of that line, that straight line between the 2 points, which is not bad, but it's not great, because the gradient here is actually more like this. So this green line here it's close, but it's not brilliant. We want to find something a bit better. So we might say to ourselves, okay, well maybe instead of that line, we'll move our point down to here, and we'll make that our second point. So if we're going to calculate that gradient, it's going to be a line like this. And we think, okay, that's better. That's a lot better than what we had before, but it's still not great. So maybe we'll come and we'll put our point in there. And now if we calculate our gradient, that line's looking a lot better. But it's still not perfect. And we don't want close in maths here, we want to be exact. So we realize then that the closer these points move to our point down here, the one that we're looking for, the more accurate our gradient's going to be. So the next logical step is, well, if this next point is on top of this point, then that's going to give us a perfect answer. The problem is, if we have 2 points on top of each other when we're doing our gradient formula, up here, where we have our rise over run, what you're going to notice is that y2 and y1 are going to be the exact same values, and x2 and x1 are going to be the exact same values as there. So we're actually going to end up with a calculation of 0 divided by 0, and that's not what we want. So we're going to cheat a little bit. We're going to try to be a little bit clever here. And what we're going to do is we're going to say, well, if this is the point we want, we're just going to call that x. X could be anything, and this is what's really nice about doing this method, is that that value of x is going to be anything. And over here, the corresponding y value, well, we know that that is f of x. So here's x, here's f of x. This is really our x1 coordinate, and this is our y1 coordinate. So we're going to have another point, and I'll just make the point over here, for example. And the value of this point is going to be the same as this x, plus just some random amount, and we'll call that h. And what h is representing is this distance here. This is h. Now, given what we said before about those points, you should be able to work out that the smaller h is, the more accurate our measurement's going to be. So if our 2 points here, we've got x and f of x, if this point here is x plus h, then that means that this point here must be f of x plus h. So that's going to give us the gradient of the straight line connecting these 2 points. So let's work that out over here. Let's write down what this would be. We're going to call this not f of x, but f dash x. That's the derivative. And that's going to equal y2 minus y1. And in this case here, y2 is f of x plus h, and y1 is f of x. Now that's going to be divided by x2, which is this point here. So that is x plus h, minus x1, which is just x. So if we go and cancel those out, you can see that we've got x and a minus x, so really that's going to disappear and that's going to disappear, and now we're just left with x down the bottom. Sorry, h down the bottom. But the problem is that we're still left with is the smaller that this h value gets, the better it's going to be. But think about what's going to happen. If h gets really, really small, say 0.01 or 0.01, first of all, f of x plus 0.001 is not that much difference to just f of x. So this number on top is essentially going to be subtracting two numbers from each other that are very, very close, which is going to leave us a tiny, tiny, tiny little number here. And when we divide it by that small number down here, that's going to make this whole thing even bigger. So it's going to get wildly out of control. And if h ever actually becomes 0, then this is going to effectively become a divide by 0, which we know we're not allowed to do. So what we're going to do is we're going to take what we call the limit as h approaches 0. That's going to stop this from being a divide by 0 issue here. We're not actually working out what's going to happen when h equals 0. We're going to work out what happens when h gets close to 0. And as you'll see in the other videos, when you get your function and you put it inside here and you work out what f of x plus h actually is, you're going to notice that it's not going to make that much of a difference. This f of x plus h, you're going to have to calculate that and expand and do a whole bunch of other things with it. Then when you subtract over here f of x, you're going to find a lot of different things cancelling out, including this h. Every term up the top that you're going to be left with will have at least one h in it, which means that you can cancel this h down the bottom and you're just going to have a single line of equation left. And then from that, you'll be very easily able to figure out what happens to that h value when it gets closer and closer to 0.